And that's the circuit we obtain, which is still very much linear. So the structure is really, really important in the graph. Without that structure, the scaling is 4 to the power of n, which is a long circuit. As an example, this glue tree plays a very important role in quantum working, but because the complexity in that area, it's not possible to get in a very efficient way to a quantum qubit or to quantum qubits, and you can get the circuit really, quite simple. So that's a Cayley tree, and then we did more layers of Cayley tree, and actually we obtained a circuit for general D Cayley tree of n branch. All right, so you can go quite far along that path, but it's very, very limited. So another type of matrices people have looked at, not us, are the sparse matrices, which has efficiently computable entries. So Jordan and Wang, they actually worked out a scheme that can implement any sparse unitary matrix. It goes like this, really simple idea. So if you have a unitary which is not Hermitian, and you embed it in such a way to make it Hermitian, because it's Hermitian, it follows, it satisfies that equality. And taking that theta to half pi, you have this identity. And therefore, in order to, if you want to implement an arbitrary sparse unitary, what you do is you implement that exponential, matrix exponential. And you can do a post-selection. No, I don't think you need to, because that naturally comes to 0, and the other qubits will give you the information of arbitrary sparse unitary operation on a general state. So that was published in 2009. And therefore, it's transformed the difficulty of doing this into doing a sparse Hamiltonian, which has been done by a lot of people, including quite a few people here. So the earlier work was proposed around 2003, and over the years, the algorithm has been optimized from polylog and to almost linear. All right. So it's a lot of work which has been done that, but it can be done. So what we looked at from a different angle, we said, okay, what about dense matrices? And again, we have to identify certain structure. General, dense, unitary, it's just, you can't do it. You can do it inefficiently, but not efficiently. So the kind of graphs we looked at are the efficiently diagonalizable. So if you can diagonalize by the spectral theorem, that's a Hamiltonian, you can always do that. The trick is to find a way of doing it efficiently. So here you can decompose it into a matrix of column vectors of H, and inside are the diagonal matrix of eigenvalues, and you do that. The simplest graphs or matrices in that group is the circulant, because the circulant, the eigenvectors are the Fourier vectors, and its eigenvalues are just the Fourier function of the first row. You can see the circulant is, you have, the element goes this way, and you just rotate. Okay? So the first row determines everything. And that first row gives you all the eigenvalues, and it's diagonal. Therefore, you just need a set of phase gates. And those vectors becomes the Fourier, and we know the quantum Fourier has the advantage of, has the exponential speed up. So I'm writing it here. So if you do it, yeah, of course, yeah, when I explain that to especially my mathematician colleagues, and they say we've done this all the time for 100 years. What's new here? What's new is if you do it classically, it's n log n, but if you do it quantum mechanically, and it's log n. Okay, so I just said this is exponential implementation, and the Fourier on either side are exponential very fast in comparison with classical ideas. In the middle, not quite so. I said it's very easy because it's diagonal. You just apply a set of phase gates. However, if we have n different, in general, that matrix would have n different eigenvalues, which means you have to have n phase gates, and immediately the exponential gain is lost. So we need to look at two types of graphs. One is, we say it only has polylog n, distinct eigenvalues, and there's plenty of them. I'll give you one of the most simple example. This is a complete graph of n vertices. Its eigenvalue, it's just 1. Okay, the rest is 0. Therefore, you only need to apply one gate for the middle and then log n, yeah, for the Fourier. And that's the circuit. So that's the Fourier, that's inverse Fourier, and that's one phase gate. And what's more is that's time independent, and you can just tune the phase depending on what time you want to look at the system, which is simple to do in your lab. And that's the exact scaling. Or your eigenvalues can be computed efficiently. And I'll give you a simplest example. This is a cycle, and if you do the spectral analysis, you will find it has n distinct eigenvalues. However, the eigenvalues follows a very simple function, and therefore you can use your quantum circuit to encode the k in superpositional states and calculate that efficiently. Therefore, this type of graphs can be done in the same way. Just before I left Perth, a student of mine gave me this paper, which is really wonderful. And this was done by two graph theorists. They proved a diamond condition for commuting graphs. Therefore, we can make composite graphs, which can be implementable. So the condition is actually quite simple. It's called a diamond because if in your graph, so color red is graph A, color blue is graph B, if you can identify such structures of two-step path. You follow the red first and then immediately follow the blue. Or you follow the blue and immediately you follow the red. If the number of such paths are equal, the proof was those two graphs would be commute. And this was the example from that paper. As I showed you earlier, the cycle graph can be implemented very efficiently. And this is almost like a line, can be implemented efficiently. And you couple them together by that diamond condition, and this graph, which is considerably more complex, can be implemented by, this is identity, there is no approximation. You can do that by doing one and after the other. And the possibilities, to me, is almost infinite. So you study what you can do well, and you somehow marry them and follow that condition, and you can make up many other structures which we'll be able to study efficiently. Okay, the last part is the non-unitary, which is a bit of a challenge. I remember many years ago when Andrew came to Perth, and you were saying, oh, we can do non-unitary just by measurement. I still remember that. So yeah, exactly. So what we want to do is to by doing measurement. It's also counterintuitive. We cannot really do arbitrary non-unitary, even if it's sparse. But we can do its inverse, still bothersome, by this one. So this was proposed in 2009, and yeah, this is one of the experimental implementation. As you can see, by using the phase estimation algorithm, you have a B, and you end up with a constant, don't worry, inverse of A of B, if you know A. So we can't implement directly A, but we can implement inverse, A inverse. Anyway, so we can do that. Arbitrary non-unitary. Thanks, Lu He. He gave me his unpublished work, and this was done very recently. And I believe this is a 2x2 non-unitary. And yes, I'll ask him. I'll ask a few others. Yao and Barry, they are all part of this work. And what's more, Lu sent me this paper as well, which is very recent, and extending this to QDITs, so arbitrary, non-unitary QDITs. That's how I, yeah. So what we did is to look at some other more general graphs or matrices. And this is the one we are currently studying. And tupelets, if you search applications of tupelets matrices, it has applications in almost every science and engineering related field, because it's like this. Okay? So it's almost like circulant, but not quite. So the trigonal, if you copy that part here, it's circulant, but if not, it's a general tupulet. Hankel is just the other way around. So whatever I describe here for the tupulets applies for Hankel matrices as well. So again, we make use of this trick and non-arbitrary random for Boson sample, for example. So we developed this package anyone can download and play with. And so this is called the CSD decomposition. So that applies for any general unitary. So the first step, I'll show you what C and S. So the C is diagonal, and S is also diagonal, but these are dense in general. You do it again. Okay? You apply the CSD to this block again and again and again until every block has this structure. And those two papers, there is an optimization procedure to make sure we get as small number of gates as possible. And this is a 8x8 unitary matrix. And that package actually prints this out. So the package has an output as a text file, so you can see the circuit immediately. And this, unfortunately, in general, is quite long. So we want to say, if we are physicists, I think I've written that comments very much. So we want to say, if we don't do it in a mathematical way, and if we look at a physical system, can we do better? Especially because it has this nice structure. So each of those decomposed block has this structure. And that's your quantum states you want to manipulate. So these four elements basically couples these two together, a dual rotation. And similarly, this, nothing else. Okay? So this four, and so on and so forth. Okay? So if we can drive the quantum system in such a way, we can do everything in parallel, many of them, and we can move them to overlap, and then apply whatever rotation is required that comes from the CSD composition, and then move them back. And just back and forth with different combination of blocks, depending on the exact structure. And we can do much better. So this is a quantum system we trimmed up, and also many people can realize this in your labs. This is what we do. I'm not going to get into the detailed physics. So basically, those states has it's a hyperfine state. The spin, the electron spin quantum number is not the number is not a good quantum number, which means that state has certain probability of the electron spin pointing upwards, certain probability of the spin pointing downwards. And then you apply polarized laser pulse, and then because the laser couples with the electron spin, it will pull the electron pointing upwards one way, and electron pointing downwards the other way. That's how we can achieve state-dependent transfer. Okay, so based on that, we looked at the possibility of driving that, and so there's some calculations of doing the steer rack. You have to control the pulse, duration, the separation, and the magnitude, phase precisely in order to achieve whatever you want to achieve. So those are the rotation matrices. Okay, and here, that's here, and you can see you can control it to arbitrary precision. So now we are ready to implement the cos and sine decomposition operator in such a way. So it's cartoon. And so first you move them, overlap, and then you apply the rotation. And then you can move them backwards, and then you excite them. And you start it over again. But each time you will be taking different blocks to overlap with different blocks. And many people are doing the photonics, integrated photonics. This was a paper we were trying to write last year or so with Michael Steele, but didn't quite finish. So you can write the structure of your graph into your photonics, and then you can move them so you can see the photon comes in and out, and when they meet, they will do some unitary transformation, and then you move them away, you do something else. So this is coin operation, translation, coin operation, and translation, and hopefully you can build them sufficiently long to realize several steps of working. Finally, over the last year, we looked at this paper, which provides another way of looking at how to design optimized, efficient quantum circuit, and it was by, you are not?
No relations. It's through Markdown.
Okay, all right, okay, so I apologize. So yeah, Michael Nelson and his co. The idea is really, really beautiful. So what we want to achieve is from a unitary matrix to a target unitary. And you can think of that in a curved space, a manifold. And because you are only allowed to do certain operations, which is single qubit, 2 qubits operations, therefore, the rest is very costly. So you put a high cost. And using that matrix, you can build up a geodesic equation. And solving that, and so this is your target, you are going from somewhere, solving that will give you the minimum geodesic distance. And Michael, his co-authors, believe that will provide a very efficient, because it's minimal in distance, and it should corresponding to a minimum number of gates. And once you get that continuous curve, you discretize it. And there are certain beautiful proofs in that paper indicating this is a possibility. So I have 2 students are looking at this. Solving that geodesic equation is challenging, especially in high dimensions. I think we are managing to do it in SU8 almost analytically, and we want to extend eventually to SU10. So to summarize, for this discrete time quantum work, we can do very well for high degree graphs with a high degree of symmetry. And we can do arbitrary sparse unitary. On this side, we can do sparse permission, and we can do if the graph can be diagonalized efficiently. And for non-unitary, still a mystery. I mean, we can't do A, but we can do A inverse. In the classical world, we can do A, but not always A inverse. It's quite non-intuitive, but that's proven that can be done. And for the other graphs, circulant, hopeless, Hancock, and there's a lot of hope to do composite graphs. Thank you very much.
Thank you. Now the session is open for questions and comments. Are there any comments, questions? Yes.
I see the graph in a circle and many waveguide involved. So experimentally, it's probably not easy to let all the waveguide interference with all interact with each other, because the distance decides the strength of the interaction. So for the big circle, so the further the long distance between two waveguides, there's probably no interaction. Do you have any comment about that?
You don't need that. You need interactions here when you brought them together. So that is referring to so here, for example, here you want to apply a local coin operation, which is only these three waveguides interacting, and then when the photon travels in those waveguides, it will come to this situation where, here, and you can see you only need those two to interact. You actually don't want every waveguide to interact. So you have this. So here is the coin operation, and then that is the translation. And you go backwards, you do the coin operation, and then you do the translation.
Yes. This is a discrete case.
Yes,
I mean the circle one you show in the very early.
Oh, very early. Okay. So which one are you referring to?
Left corner.
You mean this one? Okay, so this is a circuit model. This is not proposing any particular physical systems. So what you have, this is the hardware gate, and this is sequence of control gates. So you use the circuit model. And whether you use photonics or if you use some other quantum dots or whatever, it's fine. Yeah. So that's a quantum circuit implementation.
Comments, questions? If not the case, that's all speakers of this session.